So, welcome again to the new lecture of the course, Properties of Materials. Let us just briefly recap what we did in the last lecture. So, in the last lecture we saw determination of the resolved shear stress, basically, which was tau RSS was equal to cos phi 1 cos phi 2 into F divided by A. So, where phi 1 is the angle between tensile axis and slip plane normal, and this was the angle between tensile axis and slip direction. So, you need to take care of all the slip systems, consider all slip systems. So, if you have, let us say, tensile axis with 1 1 1 and the slip system is 1 1, let us say bar 1 and then 1 bar 1 0, then you work out the phi 1 cos phi 1 will be equal to 1 plus 1 plus minus 1. So, basically 1 into 1, 1 into 1 and 1 into minus 1, okay, divided by square root of 1 square plus 1 square plus 1 square into square root of 1 square plus 1 square plus minus 1 square, and this will work out to, you can see, 1 divided by 3. Cos phi 2 will be equal to 1 into 1 plus 1 into minus 1 plus 1 into 0 divided by square root of 1 square plus 1 square plus 1 square to square root of 1 square plus minus 1 square plus 0, and this you can see, this will become 0, this will become 0. So, essentially in this case cos phi 1 into cos phi 2 will be equal to 0. So, this is how you work out the angles, and then you work out what you call as tau RSS. And so, slip system which will be first active where tau RSS is maximum, tau RSS maximum will be the active slip system. However, for slip to occur, the tau RSS max has to exceed tau CRS for slip to occur. And then we started looking at the model for theoretical shear strength. And there we are saying that we have atomic configuration of atoms is, so you may have the touching sphere model in which atoms are placed like this, okay, and when you apply stress to this, let us say when you apply stress to this crystal, let us say it is like this, then what will happen is that, let us say the bottom layer remains the same. So, basically there will be relative movement. So, this is the state, let us say state 1, then you reach state 2 when the green atoms will now sit on top of these red atoms, okay. And then when you want to take it further, state 3 or then you have, and the green atoms will then move to again these positions. So, basically this atom will have come here, this has gone there, this has gone there, this has gone there, this has gone there. So, they are moved from one minimum. So, this is first minimum, there is a second minimum, but in between they go through a position when they are right on top of each other. So, this basically leads to a situation which is like this. So, in terms of potential energy shows a minimum at these positions. So, let us say this is 1, this, so I said this is 0, this is 1 and this is again 0. Okay. So, for 0 it will show a position like this, then again it will go to a position 0 and in between we have a position 1 where it is maximum. So, if you now plot the shear stress accordingly, the shear stress will show a variation like this. Oops, run out of space there. So, let me just something like that. So, this will correspond to, if this is the position, let us say B and this is A, then this will be at B, this will be at 0, this will be at B by 2. So, this is tau as a function of distance. So, basically we want to work out what is a simple model for theoretical shear strength. So, as a first approximation, so due to the nature of variation of energy and strength, to a first approximation one can write the shear stress as tau m into sine of 2 pi x divided by b. So, essentially this is the behavior that we are sinusoidally varying behavior. So, this is x, this is 0, this is b, this is b by 2 and this is the value, maximum value, which is tau m, or you can say tau CRSS. Okay. Okay. So, this is the as a first approximation, the stress can be written as tau is equal to tau m into sine of 2 pi x divided by b. Now, let us say the deformation is not large. So, for small displacements, for very small displacements, let us say only elastic deformation occurs and that Hooke's law is valid, that is tau is equal to g into gamma. So, shear stress is equal to shear modulus multiplied by, so let us say tau is equal to g multiplied by gamma. So, this is shear modulus and this is shear strain. This is the maximum amplitude, this is the, so 2 pi is the period, x is the at any point x. So, along direction x, a point along direction x, and b is the equilibrium distance over which complete cycle happens. All right. So, when x is equal to 1, 2 pi divided by b will be equal to 1. As a result, 2 pi will be equal to, basically this will be equal, numerator will be equal to denominator. Okay. That is when we complete the whole. So, at x is equal to b, this will be equal to 2 pi. So, tau will be equal to 0, and when x is equal to b by 2, then you can see that this will become, so at x is equal to b by 2 you can write here. So, sine 2 pi into b by 2 divided by b. So, this will be sine pi. So, this will again become 0, and when you write this x is equal to b by 4 or 3b by 4, then we can see that at x is equal to b by 4, tau will become tau m into sine of 2 pi divided by b into b by 4. So, this will be sine pi by 2, which is equal to 1. So, tau pi by b, tau the shear stress will be equal to tau m at b by 2 and 3b by 4 and so on and so forth. Okay. So, let us say to a first approximation the displacements are very small and we only have elastic regime, that is Hooke's law is valid. So, we can write tau is equal to g into gamma, and then gamma, that is the shear strain, can be written as, so this is the shear strain. So, let us say the movement is x and this is A. So, we can see that here. So, you are moving in this direction and this is the shear strain you cause. So, the shear strain will be equal to x, gamma will be equal to x divided by A for small x, otherwise it would have been tan of, it would be tan gamma. Okay. So, basically we are saying that tan gamma is equal to gamma. For similarly, for very small values of x by b, we can write sine of 2 pi x y b as 2 pi x y b. So, if we make all these approximations and plug in there, so tau will become equal to tau m into 2 pi x divided by b. So, tau m will be equal to, essentially it will be equal to g divided by 2 pi. So, we know that on one hand we are saying that tau is equal to tau m into 2 pi x divided by b, and then we say it is equal to g into x y a. So, this becomes equal to tau m becomes equal to g divided by 2 pi a into b divided by a, assuming b is approximately equal to a. So, in that case tau m is equal to g divided by 2 pi. So, maximum shear stress that is needed to move atom from one position to another is equal to g divided by 2 pi. So, g is basically the shear modulus. All right. So, this is what the value of maximum shear strength is. So, or you can say the ideal or theoretical strength of the material. So, you can say this is ideal or theoretical strength, which is g is equal to 2 pi. Now, let us say what is the value of g for metals. G varies anywhere from 20 to 150 GPa, a lot of metals. Okay. So, for a lot of metals this varies from 20 to 150 GPa. So, we can say that if this is the case, then tau m will be equal to, since equal to g divided by 2 pi, basically we are saying, let us say if this is equal to 6. So, 3 to nearly 30 GPa. So, theoretical strength is somewhere between 3 to 30 GPa. Now, what is happening here, basically you can see that atoms are bonded with respect to each other. Let us say you have top row of atoms, then you have bottom row of atoms. So, this atom and this atom, they have bonds with each other, all of them are bonded. Okay. So, all of these atoms are bonded with respect to each other. So, when you move this atom, so if you just consider this particular atom, so the atom was sitting here earlier, sorry, let me draw a black one, it was sitting here earlier. Now, it goes to this position, and what happens at this position? The separation between this and this is large. So, we can see that this bond has stretched. On the other hand, this particular bond is of different length. So, you can see that there is an increase in the energy that is required, there is an increase in the energy of the system. So, this basically what you need to do is that you need to break bond here, break the first bond, then you go to the next position, okay, and then when it goes to the next position it sits here. So, it breaks the bond with the first atom. So, first is the breaking of bond, with first neighbor, and then it re-establishes the bond with next neighbor. Okay. And in this process, this bond, the bond which was there in between, first it was like this, then it becomes like this, and then again it goes like this. So, there is a huge stretching of bonds as well as breaking of old bond and creation of new bond. So, this is what requires a lot of energy, and that is why, because of, so due to breaking of old bond and formation of new bonds, one require very large strength, theoretically speaking. So, theoretically speaking, if you calculate for a few materials like iron, let us say, or copper, or for zinc, iron is BCC, copper is FCC, zinc is HCP. So, theoretically tau m theory, let us say, is in GPa it is 12, 7 and 5. So, iron will show 12 GPa, copper will show 7 GPa and zinc will show 5 GPa. This is theoretical strength, which is very high strength. But when you look at the experimental values, so it is fine because it has to break a bond and form a new bond, and it is not just one atom, it is all the atoms which have to do. If you look at this picture, all the atoms which are present in this row, so all of these atoms, so all the atoms have to break the bonds and then re-establish, and that is why this theoretical strength is very high. However, when we see the practical values, the experimentally observed values, they are not in GPAs, they are more in MPAs. So, experimental values, they are like 15 MPa for iron, pure iron, for pure copper it is 0.5 MPa, for zinc it is 0.3 MPa. So, if you look at the ratio between the two, ratio between tau theoretical and tau experiment, the ratios is of the order of 800, 14,000 and 17,000. So, there is a large discrepancy between experimental values. So, we can understand why theoretical strength is higher, because theoretically speaking, if material is perfect, all the atoms, when they slide across each other, when the slip happens, the next row of atoms has to re-establish all the bonds that it had. So, first it has to break all the bonds with the nearest neighbors, and then it re-establishes. So, the process of breaking bonds to a first neighbor, stretching the other bonds and then going to next equilibrium position requires a lot of energy, as a result a lot of stress, and that is why the theoretical strength is very high. The question is, why is that experimental stress required is low? So, we look at certain values of various other materials. So, if you look at silver, if you look at aluminum, if you look at copper, if you look at nickel, iron, and let us say cadmium, we can look at various values. For iron, if you look at G divided by 2 pi, then it is 4. For silver it is 4.6, for aluminum it is 4.2, for copper it is nearly 7, and for nickel it is nearly 12, and so let us say it is nearly 4.5. Just write the nearest possible values. Iron it is about 13, cadmium is about 4, and if you look at the values which are experimental values, experimental sigma y, then it is in MPa. So, this is in GPa, this is in MPa, and these values are 0.37, 0.78, 0.49, this is 3.2 to 7.3, this is about 27 to 30, and this is about 70.6, all right. So, you can see there is a huge discrepancy, and this huge discrepancy of few orders of magnitude is because of presence of what we call as defects. So, this discrepancy is due to imperfect materials contain defects, and these defects basically lower the strength. So, you do not have to move. Basically, we will see that how these defects lower the strength of the materials, and presence of these defects basically causes a substantial decrease in the strength of these materials. So, this the credit of looking at why the experimental strengths are lower goes to few scientists. So, people who investigated the causes behind these discrepancies, they were Poliani, Mihaly in 1934, and then G.I. Taylor in 1934. So, and then Egon Orovon again in roughly 1934, 1930s. So, these three gentlemen basically postulated that defects named mainly dislocations are responsible for lower experimental values of yield stresses. Order of magnitudes lower than theoretical values. So, basically these are the guys who suggested that, who postulated dislocation theory and the role of dislocations in reducing the strength of these strength of materials. So, basically what these guys suggested is that when you have this piece of material, okay, and let us say the slip, this is the slip plane, okay. When you apply stress, then essentially the slip produces a step. Okay. So, this is the step which is formed. So, I mean, if you have, let us say, perfect crystal, you have an atom here, atom here, atom here, atom here, 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 you have these atoms sitting here. For this step to form, essentially these group of atoms, all of these have to move by one step here with respect to the other group of atoms. So, forming, leading to a step. Now, if the crystal was perfect, all atoms would with their neighbors, and that will lead to larger stress. So, basically this would lead to large stress. However, if the crystal was imperfect, let us say all the atoms do not have to break the bonds, you may create situation in the form of a dislocation in such a manner when all the atoms do not have to break their bonds, then the stress required is lower. So, we will see how does this work. So, first for this, so we need to look at the mechanism of how dislocations assist in reducing the stress needed for deformation or yielding. So, this is the question that we ask first. Now, so if this is the case, then in the previous picture we saw that all the atoms move. Instead of moving all the atoms, what we do is that we introduce a dislocation. So, here what you do is that you introduce a dislocation. In that case, what happens is that the bond breaking is not at the scale of all the atoms, only a few or maybe one atom needs to break its bonds with the neighbors and moves gradually from one place to another, requiring much lower stress. And now we are sort of running out of time. We will look at this in a little bit more detail in the next lecture. So, what we have done in this class is basically we looked at the estimation of theoretical stress that is required to deform a material, and we found that this value is exceptionally high, g divided by 2 pi. So, if as we know that the modulus values are of the order of few GPAs, the theoretical strength also tends to be of the order of few GPAs, which is exceptionally high as compared to when we look at the experimentally observed values, which are of the order of a few megapascals to maybe few tens of megapascals for pure metals. Of course, when you put impurities in them, they become stronger, but for pure metals the strengths are much smaller. So, and then we looked at then we sort of briefly discussed that and this is because all the atoms need to break their bonds when they are deformed. In the next class we will see how dislocations can alleviate this problem of breaking all the bonds, so that only a few bonds are needed to be broken, which leads to significant reduction in the stress that is required to deform the material. So, we will do that in the next lecture. Thank you.